Good afternoon, and thank you for joining our presentation on steam quality and how it relates to proper sterilization. I'm Scott Jacobson, Director of Healthcare Markets for Armstrong International. Today's webinar is a joint presentation developed by Armstrong and our local representative, Steam Solutions. Steam Solutions has been an Armstrong partner for over 80 years. There can be some challenges between the supply of quality steam to the sterilization area and results once it is used in the sterilization process. We hope to present some options to help improve these challenges. It's my pleasure to introduce our presenter, Aaron Biles. Aaron is located in Houston and focuses on institutional customers and supports many healthcare facilities. Before I turn it over to Aaron, let me mention a couple of housekeeping items. Your line was placed on mute when you logged in. Please utilize the Q&A link at the top right. You'll see it up at the top right, a small link there that you can open for questions. We'll leave time at the end of the webinar to address those questions. With that, let me turn over the mic to Aaron. Welcome, Aaron.
Thank you, Scott. I appreciate it. Looking forward to talking a little bit about the sterile processing side of the steam world. So with that, we'll go ahead and jump right into it. Basically, what we're going to do today is we're always going to play on the hospital thing, on the doctor thing. When you go to the doctor, it's immediately what brings you in today. And today we're going to focus on the sterile processing and some of the problems that y'all run into as it relates to wet packs, rust packs, tarnish instruments, as well as long dry times. So at least in my market, I'm out of the Houston area, and we do have the Texas Medical Center there, and pretty much in downtown. In the Texas Medical Center, steam is distributed as a utility to almost all facilities via an energy provider, a utility provider called TECO, which stands for Thermal Energy Corporation. Over in the New Orleans downtown area, they have Enwave, who does basically the same thing. They provide steam as a utility to some high rises and to some healthcare facilities and whatnot. So what's interesting though is that you have a bit of a disconnect between a plant, if you will, whether it be a district energy provider or your own boiler house. The boiler side of things, their main concern is protecting and taking care of their equipment, meaning they're going to insert amines, oxygen scavengers, removing all the dissolved solids out of the water in order to prolong their equipment, which is great. It's great for the boiler, it's great for the overall steam system, but it can cause a bit of problem when you get to the point of use, when the point of use comes in direct contact with a sterile type instrument like found in healthcare. So throughout the presentation, what we're going to try and do is we're going to try and paint a picture of the entire boiler system and the entire steam system that may not typically be provided over to the biomedical side of things or the sterile processing side of things. Kind of going to explain what causes a wet pack, what causes tarnishing, and then at the end, we're kind of going to talk about how you might be able to pull yourself out of a situation like this via different means. So we'll go ahead and dive right into it. This, although it's ultra simplistic, and I know that some of the people tuning in today probably work at multi-$100 million facilities, but effectively they can all be narrowed down to an image something similar to this. In the event that you run your own boiler, this is exactly what yours would look like. In the event you do not run your own boiler, these two lines would probably signify a location in the basement or at some point on the facility where you take steam as a utility and then you push condensate back to your utility provider, typically for a credit. At least that's how I know Enwave and TECO work. But just to start off, as simple as it gets, what is a boiler? A boiler is no different than a pot at home on the stove, except for it's got a lid on it and it starts to build pressure. It's simply phase changing water, H2O, into a vapor. If anybody's a mechanical engineering background or master's in engineering on here, I'm sure you're going to tell me that boiler water is not just H2O. You are 100% correct, but for this conversation, we're just going to make it idealistic and call it H2O. So as the system starts to build pressure, steam will naturally go to the points of use, collapse back into a liquid, phase change into a liquid, gravity drain back to some sort of a pump, and then be pushed back into the boiler system. Item one in a healthcare facility, that looks like it would probably be a domestic hot water generator. Item two would be a steam jacketed kettle, maybe in the kitchen. The next thing we're going to do is we're actually going to show that's a water molecule or one H2O traveling through the system. Notice it gets taken off, used up to heat domestic water through the D8 tank, reboiled, and then we'll go to the end of the line, condense back into the boiler. It's very high level, but it's kind of beyond the scope of this conversation to go any further. But the whole steam system is lined out right here. The one thing that this image doesn't show, admittedly, is a sterilizer. So let's just use the same train of thought, except for there's a boiler in the picture now. So again, if you don't run your own boiler, you're never going to see the boiler. But if you do have a boiler on site, then maybe it would be something like this. Again, we animated the steam just to show how it travels through the system. So initially, the steam will come out the top of the boiler, make its way into a header, and then it'll be taken off again on the top to a high pressure header. That high pressure header again will be taken off on the top through an inline separator, through a steam filter, and onto the point of use. The point of use, of course, being a sterilizer, if and only if the solenoid valve attached to the sterilizer says that it's time to get steam. That's one of the interesting points that we're going to make today, that the sterilizers themselves cannot be a place to catch condensate. They're for steam only. If anybody, before I click that, notice how interesting it's piped, or if anybody has a plumbing background, you'll notice there's so many fittings and there's so many elbows and stuff in the piping, but steam has to be respected in a different way than water, or especially different than a compressed gas like a nitrogen or a medical gas or something. So at all of these points here, on the left-hand side or here in the middle or on the bottom right-hand side, those are all places where condensate is caught in an effort to dry the steam out, because steam is constantly wanting to give up its heat energy and condense back into a liquid, so it has to be piped a bit differently. That way, your point of use, of course, your sterilizer, always has nice dry steam. So at a 30,000-foot view, we're going to talk about how sterilizers work. For you sterile processing engineers and sterile processing professionals, I'm pretty sure you know how a sterilizer works, and you're probably more qualified to talk about it than I am. But just for everybody here, we're going to, at a very high level, talk about how a sterilizer works. So first and foremost, the chamber is loaded via the door, and that means, showing that there's a door, at some point, the whole chamber is going to be open to atmospheric pressure and atmospheric humidity, non-condensable gases such as air, nitrogen, whatever is made up in our atmosphere. Once the items have been loaded into the chamber, the door has been closed, the first thing a sterilizer needs to do is it needs to get out all of that air, all of those non-condensable gases such as nitrogen, etc., CO2, that are found in our air. Steam is actually lighter than air, so it will naturally occupy the top of the chamber first and displace down all of the air and non-condensables in there. After all of the air and non-condensables has been evacuated and the chamber itself has started to heat up, as well as the jacket has started to heat up, it's going to actually start the process of sterilizing or cooking the instruments. One thing that's a bit interesting here to remember is that a sterilizer by no means is a cleaning device. All it does is sterilize the instruments after they have already been thoroughly cleaned. And so why do we want to get them hot? We want to get the instruments hot because we want to extinguish any biologic concerns. That way we can reuse the instruments in another surgery or something like that. So the last portion of a sterilizer cycle is the exhaust. We've evacuated all the air initially. We heated up the chamber with steam. Now we need to get out all of the steam. We need to begin to cool down the instruments. The chamber will then go to atmospheric pressure, or a vacuum will be pulled, and the instruments can begin to cool. The cooling time is actually, it's almost one of the forgotten things about the sterile process, in that your cooling time can tell you a whole lot about how well you're actually sterilizing the instruments and how dry they are at the point they go to exhaust. So it should be one of those values that's being tracked. The little equation down there in the bottom is so menial, but it's so incredibly important that the balance between heat and time equals results. There's no, you say your sterilizer wants 270 degrees Fahrenheit for 30 minutes. You can't put it on 400 degrees Fahrenheit for 30 seconds. It's simply not how it works. And on the same token, you can't do it for 200 degrees at 5 hours. It has to be held at a certain temperature for a certain amount of time in order to achieve the results that your guiding principles or your guiding standards require. So of the sterilizer types, there's two primary ones we're going to briefly touch on here. Is one, a gravity cycle versus a vacuum cycle. A gravity cycle, as I mentioned, simply uses the differential in the specific gravity between air and non-condensables and that of steam to displace the air. Steam is lighter than air, so it will naturally fill the top of the chamber, displace out all the air. This is good for wrapped or unwrapped processing. The other side of this would be a vacuum process, where initially, prior to the steam being introduced, a mechanical pump will pull a vacuum in the chamber and then allow steam to come in. The benefit of a vacuum system, and we're not out here pushing sterilizers, but the vacuum system is a bit quicker than the gravity system, as the mechanical pump does the work for you. One note here is the flash note here at the bottom. It is not a type of sterilizer. It's basically a type of sterilization, and it's in emergency situations where you have to have, or the process has to have some instruments in a very quick amount of time, where you have the ability to cook something that would typically take 30 minutes in maybe 7 minutes at the correct temperature. But this is not meant to be used every single time. This is not how they should always be processed. But it is something that can be done in an emergency. And most sterilizer manufacturers these days have flash settings in there for these emergency times. So this is going to be the most math, or the most kind of dry portion of the presentation. This is really going to touch on the steam stuff, which you can tell by the namesake, Steam Solutions. It's kind of what we do. So I'm going to try and be brief yet thorough. I've always been told that if you can't make it memorable, make it short, so I'll do my best on this slide. So the first thing is dryness fraction. Dryness fraction is somewhat synonymous with steam quality, because a lot of people don't live in this very niche steam world that we find ourselves in today. The dryness fraction isn't always indicative of steam quality. What it more so is, it's indicative of the amount of entrapped liquid in the steam itself, because steam is a combination of a vapor as well as a liquid. So the dryness fraction is a percentage showing how much liquid is entrapped in the steam. So shown as a percentage, if you had 95% dry steam, that would mean that you have 95% of X volume steam, 5% of X volume water or condensate or a liquid entrapped in the steam. The next one is non-condensable gases. Before I move on, actually, the importance of the dryness fraction is if you have too much liquid entrapped in your steam, it can cause a wet pack in and amongst itself without anything. You can have 0% non-condensable, 0% superheat, or 0 degrees superheat. But if your steam is too wet, you'll have so much liquid in the chamber that you won't be able to effectively evacuate it. The next point is non-condensable gases. Non-condensable gases are things such as air, nitrogen, carbon dioxide, just like we've mentioned a bit earlier in the presentation. But percent non-condensable is it's a volume equation. On the dryness fraction, it's a mass equation. In the non-condensables, it's a volume equation. So if you're to take X volume of steam and collapse that down into condensate, X percentage would be non-condensable, such as air, nitrogen, CO2. The rest would be condensate from the steam or water. Why does this matter? The non-condensable gases is almost a forgotten portion of the overall steam picture, because non-condensable gases, especially air, can cause havoc in a steam system because they actually lower the ability of steam to transfer its heat, or lowers its heat transfer coefficient. It also coats the insides of the pipes. It can cause a lot of rust and stuff like that. So the main thing is that in a sterilizer, why it's a big deal is it lowers the overall temperature of the steam and slows down the heat transfer process. The last portion here is degrees of superheat. It's the easiest one. Steam at given temperatures, or at given pressures, should be given temperatures. Just off the top of my head, I know steam at 250 psi, that's what Tico over here distributes, should be 405 degrees Fahrenheit at saturation. If you were to have steam that measured on a temperature gauge or a temperature sensor to be 415 Fahrenheit at 250 degrees, or 250 psi, that would mean you have 10 degrees of superheat. Degrees of superheat is just the amount of heat energy over what it should have, amount of sensible heat energy it has. Why that matters in a sterile processing environment is that sterile processing requires ideal saturated steam, which wants to give up its heat energy. Superheated steam doesn't actually want to give up its heat energy until it's cooled to the point of saturation. So just for a thought experiment, if we're using 250 psi steam at our 10 degrees superheat, 415 Fahrenheit, it would have to cool down 10 degrees before it even wanted to condense or give up the rest of its heat in there. Superheated steam acts much more as an ideal gas than it does as a steam vapor. So it increases the amount of time that you have to cook the sterile instruments. Again, we're definitely getting into the weeds here, but superheated steam is not something you want to find in your chamber. Although it's super counterintuitive, because you'd say, heck, if I need to get the instruments hot, I'd rather have superheated steam. I'd rather have it hotter, but it just doesn't quite work like that. So the driving guidelines, if you live in this sterile processing world, the AMI ST79 is kind of the end-all be-all, if you will. But there definitely are some others that we've run across. The Centers for Medicare and Medicaid, CMS, the Joint Commission, especially the VA Directive 11162. All of those really more or less say the same thing, and we've taken the position that AMI is sort of the backbone of that. I don't think anybody on this call is from Europe, but in Europe, EN 285 mirrors AMI or vice versa. So Armstrong did us all a favor, and they actually went on and they got the AMI standard, and we put a lot of that in here verbatim. So if you are not familiar with it, a lot of this is verbatim out of the document. So I'm not going to get too creative on these slides. I'm really more or less just going to read them and explain them to you a bit. So AMI says that in the sterile processing universe, there are two primary sources of steam: conventional plant steam coming from a district utility or your boiler house, or an electric steam generator. We personally don't see a lot of electric. They're more called a tabletop sterilizer. We don't see too many of them in my particular market. That doesn't mean they're not there, but I just don't see them all the time. Facilities are to be monitoring, controlling, and documenting the process of steam generation. So the operating words in this sentence are process of steam generation. This is a boiler side or a utility side responsibility. It is not you as the point of use. It's not your responsibility to be monitoring, controlling, and documenting how the boiler house is taking care of their steam process or their steam generation process. Next one is testing the steam against the following benchmarks. This does fall on the point of use or the sterile processing department's responsibilities. The sterile processing needs to be testing against 97 or greater % dryness fraction, meaning that over X mass, 3% of it would be liquid, 97% of it would be dry, saturated steam. Next would be non-condensable gases. Less than 3.5% is to be non-condensable gases such as air, nitrogen, CO2. And the last one is degrees of superheat, 25 C, which is equal to roughly 77 degrees Fahrenheit. One note here before we move on to the next slide is in our market, we don't see a lot of electric steam humidifiers, but people who are really chasing the best practice in the market are moving towards what we call clean steam generation, which takes either steam or superheated water as the heating media and indirectly heats reverse osmosis or DI, very clean water, to create what we call clean steam, and it's run in stainless piping, and it's really a best practice and probably where the industry will be in when we're giving this presentation in 20 years. You get away from those amines and oxygen scavengers and pipe scale and all that stuff that comes from a larger steam distribution system. So then the last portion of AMI ST79 is that the facility needs to be maintaining steam traps, boilers, and steam generators. This a bit self-explanatory. The next thing is to use inline steam filters with drip traps close to the sterilizer. It's very infrequent that we find a sterilizer that does not have a steam filter on it, but believe it or not, it does happen. So make sure those are on there. Below is a picture of the Armstrong ASF series, which is an Armstrong steam filter. And last but not least, the kind of the most important thing behind this is you can take care of all of the things noted above, but there has to be a backbone of a process or some way to document and develop a procedure around and monitor the quality, purity, and quantity. This does fall in the point of use. So manufacturer requirements. There are a lot of steam sterilizer manufacturers out there. It's kind of like car manufacturers. There's a ton of them out there, but they really more or less all do the same thing. They get you from point A to point B. Some cost more, some cost less. But a lot of them are gonna say roughly the same thing. So first and foremost, pretty much every single one of them is gonna say they want 97% dry steam or greater, which mirrors AMI ST79, EN 285, yada yada. So if you look at this note here on B, steam connections, I pulled this right out of an installation and operation manual. If your facility has house steam available, it can be used for the autoclave so long as it is condensate free and 97 to 100% saturated. The pressure should be between 50 and 80 psi dynamic with a flow rate of 180 pounds an hour. The line should be insulated and have a facility supplied drip leg trap that is 18 inches under the steam connection point. This is a very important note to remember as we move forward to the next slide, because we've actually already outlined this in the presentation, but we're going to hit on it here again. So 50 to 80 psi, the sterilizer people, they're not pressure concerned, they're temperature concerned. So if you look on the left-hand side, that we've got an example of 60 and 70 psi steam. 60 psi steam at a saturated ideal state is 307 Fahrenheit, 70 psi is 316 Fahrenheit. They're more concerned with the temperature than they are the pressure. The reason why they want 50 to 80 dynamic is there's going to be some pressure losses as you introduce the steam into the vessel, and they need a little bit of wiggle room. I've been involved in a lot of sterilizer, wet sterilizer, wet pack conversations, and I've never once heard a sterilizer manufacturer say that it was their fault. We don't represent any of them. We're very much a neutral party in this. But what ends up happening here is the facility says, we're sending you good steam. The sterilizer people say, no, you're not. And it just is a stalemate, locking horns. And what happens is the sterilizers, they become a black box. Once you've piped them in and they seem to be working initially, everybody just says, oh, don't touch it. Don't mess with it. You're going to mess it up. And they're, of course, super high dollar, super high performance pieces of equipment. So once it kind of starts to get to the point where things aren't working correctly, it's important to get validation. A lot of the sterilizers do offer their own validation that the steam coming in does not meet their requirements, or they do a steam system assessment. It's very much similar to asking the prisoners if all the doors on the prison are locked, in my opinion, but that's just my personal opinion. I think it's very important to have third-party validation. Same reason why you get your house inspected by somebody other than the person selling the house to you. So it's definitely important to bring in a third party or some other means of testing your steam quality when you get to the point where we're not really sure what is being delivered to the sterilizer. The last portion here, and we're by no means really qualified to even speak on this, but loading the sterilizer per the instructions in the instructions for usage as well as the INO is incredibly important. If it can only take 17 pounds of instruments and there's 28 pounds in there, I think I can get to the end of this one pretty quickly. It's going to be a user error, an expensive one at that, I'd imagine. So ensure that they're being loaded correctly. So we talked about a third party, and we believe that Steam Solutions and Armstrong International, your local representative, can be a real resource for helping y'all through these these sterilizer issues. We know steam, it's what we do. I mean, it's our namesake. I actually went to A&M, so I did the liberty of covering our entire territory in maroon. But what's really neat about it is we are a neutral party. We don't have any sterilizer lines. We don't represent any hospitals. We can really be the voice of reason between them. It's almost like in the Lorax, I speak for the trees. We're Texas Steam and or Steam Solutions, and we speak for the steam. We don't have a dog in the hunt, but we are here to help y'all through these issues. A lot of the times what ends up happening, at least in our experience, is the problem doesn't get addressed, but the symptom does. We're not getting wet steam anymore. Oh, we're getting terrible water hammer, but we're not getting wet steam anymore. You haven't identified the underlying issue. So what we'd like to do is the first and foremost is we'd like to just get on site with you and do a steam quality assessment and show us what's happening, tell us where your issues are and how we might be able to help. We work with people all over the Texas Medical Center, all over New Orleans area, all over the Southeast United States in general. We've probably seen this problem before. And typically the problem lies in incorrect piping. At no one's fault, but sometimes it just happens this way. And typically, it comes down to condensate drainage. That's why you get wet steam. So if you recall back a couple of slides, the sterilizer said we would like 18 inches worth of drip leg underneath the point of use. Sorry, I was trying to use the mouse here and it doesn't show up. So that arrow right there, the point of use is actually that solenoid valve. So if you remember how the steam traveled out of the boiler into the high pressure main, through the inline separator, through the steam filter, and then into the solenoid valve, that arrow would point to an 18-inch drip leg where any standing or any sitting steam that does collapse into condensate could drain to a steam trap at the bottom and keep the sterilizer steam dry. Very, very frequently, the line that is blue, where the condensate would collect, would not be there at all. It would leg right into the sterilizer, and the train of thought with some people is that, well, the sterilizer will drain the line. That's not how it works. It's going to blow condensate all over the instruments, no matter if it's how long it's been running. It's an interesting train of thought, but I don't believe in practice that it works. And the next thing is distribution headers. We see these often, so in all of the images we've showed, takeoffs, which are steam being supplied or taken from a pipe, is always at the 12 o'clock position, meaning kind of top dead center, if you will. Even when you're putting steam into the pipe, you put it into the top. When you're taking steam off, you take it off the top, because condensate, being a literal liquid, will form on the bottom of the pipe. So if you take off at the 12 o'clock position, theoretically, you will get the driest and best steam possible and leave the condensate to gravity drain to a point of trapping or drainage. Next thing is pressure reduction. We haven't touched on pressure reducing valves at all in this webinar, but they most certainly are part of the equation because no sterilizer is rated for the type of pressure you see in a distribution facility. There may be a facility out there that's running 60 psi steam, but I haven't found it. A lot of them are running 250, 200, 150 pound steam, and no sterilizer is going to be rated for that. So it has to go through what's called a pressure reducing station, which effectively takes 200 psi on the left-hand side, reduces the pressure down to 60 psi on the right-hand side. That instrument would typically be upstream of the steam filter, but downstream of your high-pressure takeoff, as well as downstream of any inline drain separators or filters that you have. They are an interesting problem in and amongst themselves that's a bit beyond this conversation here, but it is important to have them upstream of the steam filter. So we talked earlier about how you can bring in a third party. There's a couple different ways. The first way you could do it is you could do a manual steam quality test. There definitely are some benefits to doing a manual steam quality test that will give you your degrees of superheat, your non-condensable gas content, as well as your dryness fraction. The benefits of it is that one person or one team could test multiple zones over a relatively short period of time. They don't cost that much initially. And then the other one is that, say you get a wet pack today, you could potentially, depending on where you're geographically located, you could potentially get somebody on site in a couple of days to take a steam quality test. The cons are they're somewhat dangerous because you either need a 3/8 or a 1/4 inch tapping for them to tie into, or you have to hot tap the pipe, or you have to take the system down. I don't know about you, but the idea of hot tapping or drilling a live hole into a live steam line scares me down to my core. So I'd like to avoid that if it was me. But the other thing is it relies on operator experience for accurate results. The way that they're tested is a bit subjective in nature, so it's very difficult to get repeatability by the same person even on the same test, on the same position. So it's really very subjective in that. The other problem is it's non-continuous, it's a one-time test. I got pretty low grades in college. I did get a 33 on a pre-cal test my freshman year, but I ended up graduating from college. So you can't take one data point and say that person or that is indicative of the entire system or the entire situation. So I would be very hesitant to look at one single data point. The next thing is you have the ability, rather than doing a manual test, you can do an automatic or an automated steam quality testing, which is done by an instrument as opposed to somebody sticking something in your pipe. The benefits are it runs continuously, 365 days a year, 24 hours a day, 7 days a week, on the time that you've set it, minute, 5 minutes, 10 minutes, whatever. It's testing that pipe and doing its live data trending. You can integrate it right into your building automation system. And when you have the ability to trend data, you have the ability to really understand your system. You may see that every Tuesday at 4 o'clock in the morning, you get incredibly wet steam. What's happening? Oh, well, at 12 o'clock at night on Tuesdays when we take the boiler plant down, we would expect to have really bad steam following that. Okay, well then let's back up our sterile that morning to 9 a.m. until the steam's cleaned up a little bit. The next thing is repeatability. Anytime, I mean, and this is just a personal feeling, but anytime you can take the subjectivity out of a test and you can take it to a quantitative means of measuring something, your accuracy will go through the roof. Whether or not you're going to like the results is to be seen, but it will be the truth behind it. Of course, we'd be lying to ourselves if we said there weren't some bad things or some less than amazing things about an automatic steam quality testing. It does require a permanent or a semi-permanent installation. It's going to have to be installed into the pipe. They are small instruments. They can be hot tapped, but nonetheless, they will require multiple trades as well as sterile processing coordination to ensure a successful installation. And they are a bit larger initial investment. I mean, it's nominal when you think about what you're really getting for the amount of money differential, but it is a larger dollar value in most cases. So in that same vein with automatic testing, Armstrong has a couple different products that have really kind of revolutionized this industry as far as automated steam quality testing. One being the QM1. The QM1 stands for Quality Monitor 1. The Quality Monitor 1 is actually, it works at a bit higher pressure than the next one we're going to talk about. It's well suited for a distribution line to an individual sterilizer or a bank of sterilizers. The lowest pressure you can apply this on is a 60 psi line. It only monitors steam dryness fraction, but in some instances where you've got a really high-end boiler house, everything's taken care of. Your non-condensables as well as your superheat could be taken care of, but the wet factor, the dryness fraction of the steam could be your concern. It comes with all the accessories that you need. What's really neat about it, and what we've heard a lot in the field, is that the RS-485 connection for Modbus native has been really nice. These days, everybody can throw RS-485 through some sort of a gateway to talk to whatever high-end building automation system you have. It also has an optional data logger. The other product is the SQM3, which stands for Quality Monitor 3. The QM3 is really no different than the QM1, except for it has the ability to not only monitor the dryness fraction, but also the degrees of superheat, as well as the non-condensable gas content. So if you remember back to AMI ST79, the dryness fraction that they deemed acceptable was 97 to 100%. Degrees of superheat was less than 77 Fahrenheit, and the non-condensable gas content was less than 3.5%. So the ranges here are much more broad than you're going to need, but we've actually found in the field that sometimes they like to know that they're at 88% dry steam or 90% dry steam. Although they are outside of AMI, they know how far outside and what they need to correct. Again, it comes with everything that you're going to need. It can mount right to the wall, as well as it's also semi-permanent. You could move the arm as well as the unit around a bit. Again, RS-485. So with this being said, we kind of lined out what the system looks like, and hopefully we painted the picture kind of in a roundabout way that not only do we understand the bigger picture, we also understand what you're going through and what's causing the problems or what's causing the delays or the issues. And we kind of have a saying here at Steam Solutions that sterile processing, it's not a big deal until it's a big deal. Because as soon as there's a wet pack, we need you here now. We need it done. We need it taken care of now. The head of nursing, the head of sterile processing is this is not acceptable. We have to get surgery on track. I mean, there's people's lives on the line. So you cannot be too safe effectively. There's so much to lose as far as lost productivity, lost time, loss of life even. When if you could get in front of the problem on the front end, you could really mitigate a lot of exposure or risk as far as if you sit on the hospital side of things. So with that, we are going to turn it over. I'm going to turn it back over to Scott Jacobson and read through some of these questions here.
Okay, thanks, Aaron. That concludes the presentation. If you have any additional questions, please enter those on the upper right of your screen with the Q&A button. But please first note, Aaron, and my contact information. If you scroll down a screen, Aaron, bring up our, there's our contact information. You can jot down our emails, and feel free to reach out and contact us directly with questions or anything you had on the seminar. Within a few days, you'll receive a follow-up email from Armstrong with a link to the webinar for viewing, and also the opportunity to request an assessment. This would be a chance to have a steam system expert walk your system and provide a report with recommendations. So we highly recommend you consider that. If anything that Aaron touched on hit some hot buttons with you and issues you're having, that can be a great way to go through some of these things in more detail that Aaron was talking about. We also offer a number of training opportunities. Steam Solutions has a facility in Houston and one in New Orleans with demonstration equipment, including live steam piping and trapping. Very effective way to understand and more in depth of what Aaron was touching on. They offer regular seminars that are complimentary for training on steam systems, so please consider that. Secondly, Armstrong provides an online free training program with a number of related courses. There are two that are specifically related to today's presentation, one on steam quality and one on sterilization applications. You can reach those at our website, which is armstronginternational.com, and under Armstrong University. And if you have any trouble finding that, again, let Aaron or I know, and we can help you get through that. So yeah, let's we did get a question or two in. Let's take a look at those, Aaron.
Yeah, and I just want to piggyback on one thing Scott said. So we have brought a handful of hospitals as well as contractors, all sorts of end users through our training facility in New Orleans as well as Houston. The glass piping, I mean, maybe I lived a sheltered life, but when you watch invisible steam collapse into a liquid, it'll change your life. Especially if you've never seen it before. If you don't really live in this world, it's really very interesting. So I will get down to it. The first question here is, how much does an assessment cost? The assessment is complimentary. The only bad part is that you have to hang out with me or one of the other institutional people for a little while. So it is complimentary. We love to come out here. We like to meet and see what different problems people are experiencing in the market. The next one is, what healthcare facilities have adopted it? Truth be told, the earliest adopters were the VA facilities. They were following the VA directive, I believe it's 11162, that talks directly about this. We've had early successes in the Houston market as well, and the southeastern United States at some of the VAs down there, as well as a large hospital in downtown New Orleans. I initially got on it as well. They've all been pleased with it thus far. Is that they actually were really more or less surprised to see that it could be done, that you can read some of these things in a live fashion. They actually like walking up to it, especially on the SQM3, walking up to it and seeing it in real time. I mean, the QM1 is also in real time, but it just has more data on the QM3. The last one is, what's the appropriate steam pressure to be providing to a sterilizer? We touched on this a bit. It just depends. It's really more of a temperature thing, but from the installation and operation manuals that I flipped through and the instructions for use that we looked at, it was almost always 50 psi to 80 psi. And that's all about temperature, more so than it is about pressure. So if you're giving it less than 50 psi, I would say check with the INO manual and the IFU. But if it's somewhere in the 60s, I'd assume you're probably taken care of.
Okay, that looks like it's it for the questions. So we look forward to hearing from you and encourage you to reach out to Aaron or myself. And yeah, we thank you for your time today and look forward to working with you in the future. Thank you.
Thank you.